How do neural networks store and retrieve information? The standard answer is feature combination. Networks detect simple patterns and hierarchically combine them into complex concepts. But this paper argues for something deeper: feature recall. Neural networks don't just combine what they see, they retrieve stored knowledge triggered by their inputs. Consider how ChatGPT completes the sentence, "Michael Jordan plays basketball." The model receives Michael and Jordan as input tokens. But where does the basketball information come from? It's not in the input prompt. Instead, the model retrieves this fact from its weights. This is different from combining features. It's recalling stored knowledge. A standard mechanistic interpretability view is feature combination. In this model, each layer detects increasingly abstract patterns. Early layers find edges, middle layers find shapes, and later layers find objects. Each layer's output is a linear combination of its inputs. The network builds up understanding hierarchically. But feature combination has a problem. It doesn't explain factual retrieval well. If you don't have basketball in your input, how can combining features produce it? You can't make something out of nothing. This suggests a different mechanism. The network stores basketball information in its weights and retrieves it when it sees Michael Jordan. Feature recall is a general mechanism in neural networks. The core insight: a linear projection can be read as retrieving stored information, scaled by input activations. When a Michael Jordan feature becomes active, the weights associated with that feature are activated, retrieving basketball and bulls. The weights store information like a lookup table. Here's the key insight: a simple matrix multiplication can be interpreted two ways. First, as feature combination. Each output feature is a weighted sum of input features, with columns of the weight matrix defining patterns. Second, as feature recall. Each input feature activates its own row of the weight matrix, retrieving associated information. Both interpretations describe the exact same computation. Feature recall applies beyond language models. In a convolutional neural network detecting shapes, the feature combination view says, look for corners to detect squares, look for curves to detect circles. The feature recall view says, the detector weights store what a circle pattern looks like, and input activations retrieve that stored pattern. Same computation, different understanding. Feature recall operates at two levels. Factual recall: Michael Jordan retrieves the contingent fact that he plays basketball, something that could have been different. Conceptual recall: Bachelor retrieves the conceptual truth that the person is unmarried, something that's true by definition. Both are retrieved from weights, but differ in their nature and necessity. The key difference: in feature combination, the weights define patterns to detect from the input. In feature recall, the weights store information that the input triggers. Think of it this way: combination is like asking, what patterns do I see? Recall is like asking, what do I know about what I see? It's a shift of focus from inputs to weights. How do we identify feature recall in real networks? One approach: find inputs that activate a particular feature strongly. Then examine the weights associated with that feature. Do those weights consistently produce outputs that are conceptually or factually related to the input? If so, you found recall. This requires careful ablation and probing studies. This framework offers philosophers a new conceptual tool for understanding deep learning. It challenges the assumption that neural networks are purely feature combination machines that learn hierarchical abstractions. Instead, they also retrieve and store information. This has implications for how we think about neural network understanding and knowledge representation. This work opens several research directions. First, systematically identifying cases of feature recall across architectures. Second, understanding how recall and combination interact in deep networks. Third, using this framework to improve interpretability and mechanistic understanding. Fourth, exploring whether feature recall might enable new techniques for model editing or alignment. This paper complements recent mechanistic interpretability work on how LLMs store and retrieve facts. Studies have shown that specific neurons and circuits store biographical facts, that these facts can be edited, and that they are retrieved through attention and multi-layer perceptron layers. Feature recall provides a unified conceptual framework for understanding these empirical findings. Feature recall is a unified way to understand how neural networks retrieve stored information. It applies across architectures and complements the feature combination paradigm. By focusing on weights as storing information rather than detecting patterns, we gain new insights into deep learning mechanistic interpretability. This conceptual framework opens new empirical directions for understanding how models work.